Hello everyone, I am Punyakeerthi BL. Welcome to my Generative AI Basics series. In this series, we will learn the basic concepts of Generative AI in a simple and easy way. Let's get started with today's session. Today's topic is Mini Project, a semantic search engine using embeddings. Let's start with introduction. So, when people hear the word search engine, they usually think about searching with keywords. For example, search for car, results containing the word car. Search for Python, results containing Python. Traditional search depends heavily on exact words, but modern AI search works differently. Instead of matching words, it tries to understand the meaning of the sentence. This approach is called semantic search. Semantic search allows user to ask questions naturally, even if the exact words are different from those stored in the database. For example, suppose our fact database contains how I can reset my account password. A user can search for I forgot my login credentials. Even though words, password and credentials are different, semantic search understands that both sentences discuss the same topic and returns the correct result. This is possible because both sentences are converted into embeddings, which capture their meaning. In this lesson, we will build a complete mini semantic search engine from scratch using Python. No database, no vector database, everything will run in memory. By the end of this lesson, you will understand the complete semantic search workflow, which is used in Retrieval-Augmented Generation, which commonly we call it as the RAG, AI assistants, document search systems, and recommendation engines. So, what we will build in this lesson? Our application will perform the following tasks. The overall workflow looks like this. It is a simple fact retrieval using embeddings. So, the start point is first we need to create a small fact database, a list of question and answer pairs. But in our example, we are just creating a set of fact. Then this fact data set we need to convert every fact into an embedding. Fact content transformed into vector representation. Then we need to store those embeddings in memory, so vector saved in RAM for fast access. Later we need to accept a user question, so wait for the query input. Later that question, convert the question into an embedding, query transform into a vector. Then compare the query with every stored embedding. Calculate the similarity score, for example using Cosine Similarity. Then find the most similar facts, rank by similarity scores. Once the scores are sorted, then we need to display the top 3 matching results. So show original facts to the user. That is the end. This is overall workflow. Let's start with steps. The step 1 is create the fact data set. So before searching anything, we need some data. Imagine a company website containing frequently asked questions that we call it as fact. Example topics: password reset, shipping, orders, refunds, billing, product information, technical support. Our semantic search engine will search through these facts. Instead of using real database, we will create a Python list as of now. So example dataset look like this: fact data with questions like how do I reset my password and all. So I already copied this one. So let's go to Google Colab, which is a code to run. So I created a list called fact data which contains these values. When we run, we printed fact data, these many questions we took. So in real world, maybe for the complete project, imagine having 50 different facts covering various topics. Each item is simply a sentence. But in our example, we took only this sample data set. So why use diverse questions? Next topic is why we need to use these diverse questions, because if every fact talks about the same thing, semantic search becomes less interesting. Instead, include multiple categories such as accounts, payments, orders, shipping, refunds, security, login, products, technical issues, membership. The more diverse the dataset, the better you can observe how semantic search distinguishes between different meanings. So next step is step 2, generate embeddings. Computers cannot understand raw text directly. They understand numbers. Therefore, every sentence must be converted into a numerical vector called an embedding. An embedding captures the meaning of a sentence in high dimensional space. For example, here we have a text called reset my password. When we convert it into these embeddings, these are the values we can see. This is just an example. For another sentence, we can have I forgot my login password is a text. So that will be converted into vectors like this 0.23. Vectors and embeddings are same. All the words are different. Their vectors will be also close together because they have similar meanings. So next is using sentence transformers. We can use the sentence transformers library to generate embeddings. So first we need to install pip install sentence transforms. Once the sentence transformers installed, we need to import the model. So we need to import a model. This model lightweight, fast, widely used for semantic search. So here the model is All-Mini LLM L6 V2. So I'm copying this one and let's load this. So when we run this, it takes some seconds to load. So now we're loading waits and it's loaded. So let's print what model contains just after loading. So what I will do, I will print this model. So it loads the weights, then we'll have to instant transformer. So embedding dimension is 384 by default. So polling mode is mean and include prompt is true. This much model is ready with loaded now. So this model we already know. So then we have to generate embeddings for all facts. So fact embeddings, fact data we already loaded, right? Fact data is a list. As of now, we are able to see fact data is loaded. So let's create a embeddings. So fact embeddings model dot encode fact data. So what I will do, I will print fact embeddings. So if I print, it will be a large number of values. You are able to see fact data is printed here like this. Okay, so let's understand. Now every fact has been converted into a vector. Conceptually, it will look like this: fact 1, the embedding vector; fact 2, embedding vector; fact 3, embedding vector. The corresponding embedding vector values will be stored. The embedding vector values look like this in the real world. So from all our questions are there, each question is converted into different embedding vectors. Instead of text alone, our search engine now has numerical representation of meaning. Let's understand what model dot encode does. So sentence is equal to how do I reset my password. So encoding it, embedding is equal to model dot encode sentence. If I pass this one, what happens? So the output will be a long list of floating pointing numbers. Example like this, we are able to see here. We created this long list of embedding values. Typically, the embedding has hundreds of dimensions. For example, 384 All-Mini LLM6. So you are able to see here for embedding dimension is 384, whichever we have used All-Mini LLM6, right? That's why we are getting like this. This has hundreds of dimensions. Each number contributes to be representing the sentence semantic meaning. You do not need to interpret each number individually. Instead, think of entire vector as a fingerprint representing the sentence. Okay, next step is step 3, store embeddings in memory. Since this is a small project, we do not need a vector database like FIAS or Pinecone. We can simply store everything in a Python dictionary. So this is our fact store. Okay, each and every fact store we can generate and we can store. So what I will do once it is done, print and embedding. We can print like this. Fact store and its values will be printed. So it's giving error because like this. So when I run, see these many values netters. For each questions we created, how long does shipping take? The embed will be created like this. So for each question we created the embeddings. So now each question fact maps directly to its embedding. The structure look like this: fact sentence and embedding vector. We are able to see here for question, one question, how long does shipping take? This is our fact and its corresponding embedding. Once this is done, this makes it easy to retrieve the embedding associated with any fact. So why we need to store the embeddings? If we generated embeddings every time a user searched, the application would be slower. Instead, we generate them once and reuse them. This is much more efficient. So we completed step 3. Next part is step 4. Accept a user query. Now we simulate a user asking question. So like this. This is normal Python code query. Input, enter your question. So let's take this and run. When I run, let's go with theoretically. So example inputs are I forgot my password, how I can get my invoice, track my package. These are the questions are there. Let's take one question. I forgot my password, and I will enter here. So when we enter your question, I forgot password. So till whatever we enter, it is a text. These inputs are still plain text. We must convert them into embeddings. We need to take the question. Then once the question is input is given by the user, that query will should be converted to embeddings. That will be helpful to search in the already generated fact embeddings. So convert query into an embedding. Query embedding is equal to model.encode query. Okay. So query embedding is generated. So if I print that query embedding, that will be a list of values, same how it look like, right? So this has lot of values will be printed. See, these many values are printed now. So these are generated for query. Now the user's question is represented in the same vector space as the facts, making meaningful comparison possible. That is step 4 is completed. Next is step 5, compare using Cosine similarity. We now need to measure how similar the query is to every fact. The most common metric is Cosine similarity. Cosine similarity measures the angle between two vectors. Similar meaning vectors point in nearly the same direction, similarly close to 1. Unrelated meaning vectors point in different directions, similarity closer to 0. Opposite meaning rare for embeddings, similarity can be negative. So visualize it like this: similar sentences, vector A, vector B, small angle, similarity is equal to 1.0. Different sentences, vector A, vector B, 90-degree angle, similarity is not 0. So equal to 0. Okay, let's go with some code example. This is how we can search in the embeddings and Cosine similarity will be loaded. So I'm loading. First understand this. Import the Cosine similarity function from the scikit-learn. So Cosine similarity measures how similar two vectors are. From scikit-learn matrix pairwise import Cosine similarity. It is imported. Then create an empty list to store each fact and its similarity score. Scores is equal to like this. Then loop through every fact and its corresponding embedding vector, where we store fact store.items, which contains fact and embeddings. Then compare user's query embedding with the current fact embedding. So Cosine similarity returns a today array. Similarity score, query embedding. Okay, query embedding which converts the query vector into 2D array, one sample. Embedding converts the fact vector into a 2D array, one sample. So 0, 0 extract the actual similarity value. Similarity is equal to Cosine similarity, and query embedding and embeddings 0, 0 we are passing. So store the fact along with the similarity score like this: scores.append fact and its similarity score. Once this is completed, so what we will do, iterate through every stored fact, compare its embedding with query embedding, then calculate a similarity score, store the fact and its score together. At the end, scores contains a list of tuples. Let's run this. So we can't print. So we run this, the code is compiled successfully. Next step is sort the results. Now we arrange the facts from the highest similarity score to lowest. We are using lambda here. So the next step is sorting is started. Scores are sorted now. So now explanation: key lambda item tells Python to sort using the similarity score, the second element in the each tuple. That is what we are doing here. Then reverse is equal to true means ensure the highest score appears first. Then return the top results. This is the top result. How to return top 3 results we need, because when we enter a question, top 3 answers what we will get, that we will enter. So top results will print. So once the top scores are extracted, what we are going to do, that top results will be printed now. So for our question, what the question we have asked is in our embedding encode. So all mini LLM we did. So our question is user query pack embeddings we created. So query embeddings created. So our question is enter your question. I forgot my password is my question. So for that question, so now in our result we will get, see, score top matching questions are: how do I reset my password? Then how can I change my email address? How do I cancel my subscription? These are the questions we got. So the score, the most highest score is 0.780, but the top 3 we need, but these are lesser than whatever 7.80 we got. This is related question. We take that one and we can answer. So in this way, we can output top matching results we get. Even if the user's wording differs, the search engine identifies the most semantically similar facts. So the complete end-to-end example is here. We imported and loaded the model, then pack dataset created and generate embeddings, store embeddings, then user query, then query embeddings model dot encode. So results will be stored. So results dot key lambda x, then we print the top 3 results. This is how project we entered. So we worked on this project, right? So why this project matters, that is the question. So although this project is small, it demonstrates the core idea behind the many modern AI applications. The same workflow is used in AI powered chatbots, retrieval augmented generation, intelligent document search, enterprise knowledge databases, customer support systems, product recommendation engines, question answering applications, and all. The main difference in real world system is scale. Instead of searching through 50 facts in memory, production systems may search millions of documents using specialized vector database such as FIAS, Milvus, Pinecone, or ChromaDB for faster retrieval. So best practices are, as your projects grow, keep these practices in mind. Generate embeddings only once and reuse them instead of recalculating. Choosing an embedding model that balances accuracy and speed for your use case. Normalize vectors if your similarity library expects normalized inputs. Use a vector database for large datasets to improve search performance. Test with different user questions to verify the semantically related queries return relevant results. So summaries. In this lesson, you learned how to build simple semantic search engine from scratch using embeddings. You explored how to create dataset of facts, convert text into embeddings using pre-trained model, store embeddings in memory using Python data structures, convert user queries into embeddings, measure semantic similarity with Cosine similarity, rank search results based on similarity scores, return the top 3 most relevant matches. These concepts form the foundation of modern AI search systems, retrieval augmented generation, vector databases, and intelligent assignments. Once you understand this workflow, you will be well prepared to build more advanced applications such as document search, knowledge retrieval systems, and AI-powered chatbots. So that is the end. Thank you for watching today's session. This video is part of Generative AI Basics series. I am Punyakeerthi BL. If you found this video helpful, please like, share, and subscribe to my channel for more videos. Thank you and see you in the next video. Happy learning.